All right, so today, in particular, the second half of the lecture today, we're going to do some of the hardest concepts that we've done so far, and also some of the most important concepts that we've done so far. So I just want to give you a heads up on that. All right, so last time we had solved the Schrodinger equation. We had solved the Schrodinger equation for the binding energies of the electron to the nucleus. That means if I write the generic Schrodinger equation down here, what we found was what this E was. And we found that it had a nice analytical form, that the energies, the allowed binding energies, were quantized. They were quantized by that principal quantum number n. And so we can write those allowed energies as E sub n is minus R sub h over n squared. All right, so n is this principal quantum number. And n runs from 1, 2, all the way up to infinity. All right, today what we're going to do is we're going to look at the solutions to the Schrodinger equation for this, for the wave function, for the wave. And remember, we said that the wave, in some way, represents our electron. And today we are going to talk about exactly what is the meaning of the wave function. But before we do that, I have to tell you that when you go to solve the Schrodinger equation for the wave function here, what happens is that two more quantum numbers pop out. All right? And one of the quantum numbers that pop out in the solution to the wave function, for the wave function, is a quantum number we call L. L is the angular momentum quantum number. It's called the angular momentum quantum number because it in fact determines how much angular momentum the electron has. It is a quantum number, which means it has allowed values, very specific values. The allowed values of L are the following. They are 0. Unlike n, the lowest value that L can have is 0. 0, 1, 2, 3, all the way up. But it's got a limit. L's got a limit. The limit is n minus 1. So L can never be larger than n minus 1. It's tied to the principal quantum number. Why is it tied to the principal quantum number? Well, notice that only the principal quantum number tells you about the binding energy. It tells you about the total energy of this electron interacting with the nucleus. Whereas the L, the quantum number L, the angular momentum quantum number, it determines how much angular momentum the electron has. And in a classical picture, you may be familiar with the fact that if something's got angular momentum, it has rotational kinetic energy. And since the total energy is that rotational kinetic energy plus potential energy, well, then L is never going to be as large as n, because otherwise then the electron would only have rotational kinetic energy and no potential energy, and that wouldn't work, right? So that's why there's a limit here to L. It is as large as n minus 1, because you have to leave some energy to be potential energy here, right? Okay. And then finally, we have a third quantum number. And that third quantum number we call M. And it's the magnetic quantum number. And it's called magnetic because, in fact, it does determine the behavior of an atom in a magnetic field, although we're actually not going to take a look at that. But more specifically, what m is the z component of the angular momentum. All right? It's the z component of the angular momentum. And its allowed values are the following. Its allowed values are m equals 0. All right, so just like L, it can have a value of 0. Plus 1, plus 2, all the way up to plus L. All right? So, hey, look at this. The magnetic quantum number is tied to the angular momentum quantum number. Why? Well, because this is the z component of the angular momentum, or it dictates the z component of the angular momentum. L dictated the total angular momentum. Well, the z component of the angular momentum is never going to be bigger than the total angular momentum, so that's why m is tied to L. And of course, when we talk about a component, hey, we're going to have a direction here too. And so these quantum number m can be 0, plus or minus L, plus or minus 1, plus or minus 2, all the way down to plus or minus L. All right? So that is it. We've got to have 3 quantum numbers here to really explain our system. All right? The reason we have 3 quantum numbers is because we have a 3-dimensional system. So it a little bit makes sense that you've got to have 3 quantum numbers to really describe the hydrogen atom here. All right? And then the consequence of having these 3 quantum numbers, when you solve that differential equation, remember we talked last time where those quantum numbers come from. When you solve a differential equation, as you will when you do 1803, right? Those quantum numbers come from imposing these boundary conditions on your differential equation. Those boundary conditions make a generic or general differential equation specific to the problem you're working on. And when you do that, those quantum numbers fall right out. All right? And again, we believe them to be true because they agree with our observations of nature. All right? Okay. So now we got to deal with 3 quantum numbers that are going to have to then describe these states that we talked about last time. So, for example, we talked about the ground state. N is equal to 1 here. But what I'm saying to you now is that there are a few more quantum numbers that we have to add to label that ground state correctly, or to label it completely. And I just said if n is equal to 1, well, then we learned about L here. L, the largest value it can have, is n minus 1. So we have a quantum number L that's tied here. And that quantum number is 0. L is equal to 0. And we just learned that we have a 3rd quantum number m, and the greatest value that m can have is plus L. So if L is 0, then m is 0. Oh, can you see that? Yeah? Okay. And so therefore, our ground state, the label that we got to put to our ground state, is the 1, 0, 0 state. All right, so we're expanding our definition of the label of that state. Yes, the last time it was n equal 1. Now it's 1, 0, 0. And then if we have an electron in that 1, 0, 0 state, then we're going to have a wave function that describes that electron. That electron is going to be represented by a wave function. That wave function is psi 1, 0, 0. All right. The energy of that 1, 0, 0 state is minus the Rydberg constant over 1 squared, just like we had last time. All right, now suppose we have the first excited state, which was n equal 2 as we looked at last time. If n is equal to 2, what is the smallest value that L can have? Smallest value that L can have? 0. And if L is equal to 0, what's the only value M can have? 0. So we have now a state that is the 2, 0, 0 state. And if you have an electron in the 2, 0, 0 state, well, we're going to describe that electron by a wave function that we're going to label psi 2, 0, 0. And the energy of that state we saw last time minus the Rydberg constant over 4. All right, but if n is equal to 2, we also just saw that the quantum number L can have another value, and that is 1. And if L is equal to 1, what is the largest value that M can have? 1. And so we've got another state here. It's the 2, 1, 0, 2, 1, 1 state. And if you got an electron in the 2, 1, 1 state, hey, that electron is going to be described by a wave function that we're going to call the psi 2, 1, 1 state. The psi 2, 1, 1 wave function. Notice that the energy of this state is still minus the Rydberg constant over 4. It is the same as the 2, 0, 0 state. These two states are said to be degenerate. Degenerate means have the same energy. All right, so if n is equal to 2, and then L, of course, can be equal to 1, what's the next smaller value that M can have? 0. So we have a 2, 1, 0 state. If an electron is in that state, the wave function describing that electron is 2, 1, 0. Again, the energy here is minus the Rydberg constant over 4. Same energy, because the energy is only dictated by the n quantum number. And then finally, what's the smallest value M can be if you have n equal 2, L equal 1? Negative 1. So we have a 2, 1, negative 1 state. The wave function describing that electron in that state is the psi 2, 1, minus 1 wave function. All right. So now I describe the electrons in these states by these wave functions psi. But there is another language, as I alluded to last time, another language that is used to describe the wave functions. And that language is this orbital language. Right? So we talked last time how an orbital is nothing other than a wave function. Right? It is the solution to the Schrodinger equation for the hydrogen atom. It is actually the spatial part of the wave function, meaning there's another part of the wave function called the spin part, but we'll look at that a little bit later. All right? Okay, and how are we going to label these wave functions in the orbital language? Well, we're going to label them by the principal quantum number n, and of course, the angular momentum quantum number L, and then the subscript here m for the magnetic quantum number. But what we do is, instead of using the actual value of L, we have a code, we got a letter code. So, for example, if L is equal to 0, we call that the S orbital. So in the case of the 1, 0, 0 state, if you have an electron in that state, the wave function that describes that electron is the 1s orbital, or the psi 1, 0, 0 wave function. All right, this is the principal quantum number. This is the code S for L is equal to 0. And then likewise, in the 2, 0, 0 state, the wave function that describes that electron will be 2s, because here's the n equal 2, and then our code for L equals 0 is S. Now, when L is equal to 1, again, we don't use L equal 1, we use a letter. That letter is P. We call that a P orbital. So this state here, the 2, 1, 1 state, is going to be a 2p wave function, or the electron in it is going to be represented by this 2p wave function. Same thing for this. Same thing for this state. They're all 2p's, okay? Because L is equal to 1 for all these three states, and N is equal to 2. Now, if I had here an angular momentum quantum number of 2, we'd call that a d orbital. If I had one that L is equal to 3, I'd call that an f orbital, and so on and so forth. All right. But now, what I haven't said anything about yet is the m quantum number here. All right, and again, we've got a code for this. We're actually not going to use the number m, we're going to use some letters. And the code is that when m is equal to 0, we're going to put a z subscript here on this p orbital designation when m is equal to 0. When m is equal to 1, hey, we're going to put an x subscript on this p designation. And when m is equal to -1, we're going to put a y subscript on this designation. Okay? Now, I should tell you that what I just did here is not actually correct. All right? In other words, m is equal to 1 isn't really the x subscript, and m is equal to -1 isn't really the y subscript. The reason is because these 2p wave functions, when m is 1 and m is -1, hey, they're complex. They're complex functions. And what we do is that we do some linear combination of the m equal 1 and m equal -1 wave functions to get what we call the px wave function and the py wave function. One is a plus linear combination, one's a negative linear combination. You're not responsible for that. Therefore, you're not responsible for knowing when m is equal to 1, we have an x, and m is equal to -1, we have a y. You are responsible for knowing when m is equal to 0, you have a z subscript here. Okay? Okay, now, I should make one other point here. And that is, you see, I don't have a subscript here for m on the s orbitals. Well, in an s state, when L is equal to 0, there's only one possible value of m, which is 0, right? And so we just leave out that subscript. We don't put a z here on the s designation. Okay? All right. So, what does this mean? The fact that we got these, now, these extra quantum numbers. Well, it means we have extra states. And these states, actually, they'll have the same energies that we saw last time. All right? But let's try to expand that a little bit and draw an energy level diagram so that we really understand what's going on. All right, so here's my energy level diagram, energy going up this way. And when n is equal to 1 then, right, our quantum numbers, the most complete description here is the 100 state. And the electron in that state has a wave function that's describing that electron, or that represents that electron. We call that the 1s wave function. That's the energy. All right. When n is equal to 2, you see now we've got 4 different states. 4 different states that are all the same energy. 2s, 2py, 2pz, 2px. They have all the same energy. They are degenerate. Again, degenerate means having the same energy. And in general, what we've got is n squared degenerate states at each n. Okay? So these have all the same energy. They differ in how much angular momentum the electron has and how much angular momentum the electron has in the z direction if it were in the presence of a magnetic field. Okay? but they have the same energy because energy is only dictated by the n quantum number. All right. So now, when n is equal to 3, how many degenerate states do we have? 9. Here they are, right? The energy is minus 1/9, the Rydberg constant. Here are the 9 degenerate states. 3s, 3py, 3pz, 3px. Hey, that pattern just reproduces 2s, 2py, 2pz, 2px. So we won't go through those. Right. But now we've got some extra states here. Again, their quantum numbers are all 3 for n. But when n is 3, the largest value of L is 2. And so all of these states here have L is equal to 2. And our code for L is equal to 2 were these D states, or these, if you have an electron in those states, it's represented by a 3D wave function. Okay? Okay. But now, the reason these 3D wave functions differ is because they have different amounts of angular momentum in the z component. They have different values of m. So, if n is equal to 3, L is equal to 2, the smallest value that m can have is minus 2, right? Okay. And then I'm going to just call, when m is equal to minus 2, I'm going to call that the xy here in the subscript. When m is equal to minus 1, I'm going to put a yz in this subscript. When m is equal to 0, I'm going to put a z squared in this subscript. That's going to be my code for m is equal to 0. In the case of the 3D orbitals, the 3D wave functions, I'm going to put a z squared in that subscript. And then when m is equal to 1, I'm putting an xz. And when m is equal to 2, an x squared minus y squared. It's off the screen a little bit, but I think it's in your notes. Okay, again, you are not responsible for knowing when m is minus 2, this is xy. When m is minus 1, this is yz, because that isn't strictly correct. We, again, got complex functions. We're making them real, and we're taking linear combinations. You are responsible for knowing that when m is equal to 0 in a 3D state, this subscript here is z squared. All right, so when m is equal to 0 in a 2p state, that's a z subscript. When m is equal to 0 in a 3D state, that's a z squared subscript. You will look at these 3D states more in detail when we talk about transition metals in the second half of the course with Professor Drennan. All right, so that's our energy level diagram. Everybody okay with this? Questions? Okay. All right, so now we found these 2 other quantum numbers. We got 3 quantum numbers. We know how to label the states, and we know how to label the wave functions that describe the electrons in these states. But now it's time to talk about what a wave function really means, or how exactly does a wave function represent this particle, this electron? You know, how do you interpret the wave function? All right? And the answer is you don't. The answer is that wave function is the wave function. Okay? It is one of these concepts that you can't or you don't have a ready classical analogy. It's one of these concepts that you don't experience in your everyday life, and so you can't say it's like this, right? Because within your everyday world, there's nothing to draw a correct analogy to, all right? However, the wave function squared does have a physical interpretation that is meaningful in your environment, okay? And that is that this wave function squared, and let me just write it out here now in its full glory. Remember, this wave function we're going to denote by 3 quantum numbers, n, l, and m, and it's a function of r, theta, and phi, right? If I take this wave function and I square it, the interpretation of that wave function squared is that it is the probability density. That is, it is a probability per unit volume, right? A density is always per unit volume. So it's a probability per unit volume. Okay. Where did that come from? Good question. You know, soon after Schrodinger wrote down his wave equations, there's a lot of discussion in the scientific community about what does psi really mean? What's the interpretation of psi? And there were a lot of interpretations given, a lot of explanations given. But finally, one very clever scientist by the name of Max Born said, you know, if I think of psi squared as a probability density, well, then I can understand the predictions that the Schrodinger equation makes. Okay? So psi squared is an interpretation, right? He said, if I think of psi squared as the probability per unit volume, and then I go and analyze all of the results of solving the Schrodinger equation in terms of that concept, that it's a probability density, then things make sense, and those predictions agree with my observations. Hey, you know what? That's it. There's no derivation here of psi squared. Psi squared is just that. It is an assumption. It is an ansatz. It is an interpretation. But you know what? You use that interpretation, and that makes predictions that agree with our observations, and there are no observations that even hint that that interpretation isn't correct. Okay? But that's it. You know, you don't go any further. There's no derivation of this, right? This is an interpretation. It's a probability density. Okay? All right. Well, this gentleman, Max Born, really very clever scientist. Max Born is the same Born of something called the Born-Oppenheimer approximation that maybe some of you know about. It's the same Born of the distorted wave Born approximation, which you probably nobody knows about. Okay? But I got to tell you that despite the fact that Max Born has all of these accomplishments, the interpretation of psi squared as a probability density, the Born-Oppenheimer approximation, the distorted wave Born approximation, despite all of those accomplishments, he is best known for being the grandfather of Olivia Newton-John. That is true. They're actually... a couple of weeks ago in the Boston Globe, and I guess papers throughout the country, has a magazine called Parade Magazine, and it actually had an article about Olivia Newton-John. Olivia Newton-John, somebody's going, who's Olivia Newton-John? That's just an indication of how old I am, right? Olivia Newton-John is a singer. Greece, right? What? Yeah, right. It was interesting. The Boston Globe a few weeks ago in Parade Magazine, there was an article on her and mentioned that her grandfather was Max Born. Didn't say anything about Max Born after that, but did mention that, okay? All right, so now you know what psi squared is. It's a probability density. Hey, you and I, we can understand that. Psi squared, we can understand that. It's a probability density. But what I want to really emphasize here is that it is a probability density. It is not probability. It is probability per unit volume. That's important. In a moment, we're going to look at a quantity that is a probability. But this is a probability density. All right, you got to get the units correct here. All right. So, how can we use that to understand something about where the electron is in an atom? Well, let's do that. On the slide here. Yeah, we'll kill those lights. Okay. So, probability density. What I'm going to do is I'm going to represent the probability density here by a density dot diagram. So I'm going to take my 1s orbital, okay, my 1s wave function, or my psi 100 wave function, and I'm going to square it. And then I'm going to take the results of that squared function and plot it as a dot diagram here, where the density of the dots is proportional to the probability density. So the darker the dots, the higher the probability density. And as the dots get more and more dispersed, right, the probability density is getting smaller. So I did that for my 1s wave function, squared the 1s wave function, and plotted it here on an x, y, z. Yeah. Oh, I got the x and the y turned around. Okay. That's all right. I plotted it here. What you can see is that the probability density is a maximum at the origin, at the nucleus, and that it decays equally in all directions. It's isotropic. There's no angular dependence. It's spherically symmetric. And that you can also see nicely if you look at the actual plot of the wave function, not psi squared now, the wave function, which I'm plotting here. This is the wave function, and I'm plotting it versus r. Actually, what I'm plotting it here is as r over this, something called the A naught. A naught's a constant. A naught is called the Bohr radius. A naught is about a half an angstrom. I'll explain to you where A naught comes from in a little bit, but right now it's just a constant. Here's the actual form of that wave function. Okay? Hey, it's pretty simple. This stuff right in here, this is all a constant, right? Just 1 over pi A naught cubed. I said this was about a half an angstrom. And then the important part is right here. It's a decaying exponential in r, e to the minus r over A naught. And so the wave function starts out at some high finite value at r is equal to 0, and it drops off exponentially as r goes to infinity. That's what we're plotting And you can see that reflected here. When you square this, you can see that reflected in that probability density. All right? So what does it tell me? It tells me that the probability density is highest at the nucleus and drops off in an exponential fashion equally in all directions. This is spherically symmetric. Okay, we're going to say some more about where's the electron in a moment after we go through not only 1s but 2s and 3s. All right? So here I plotted the 2s wave function. I took the 2s wave function, I squared it. And so I got values as a function of r. And again, the density of the dots is proportional to that wave function squared. And again, what do you see? You see that the probability density is largest at the origin. And that it decays, again, equally in all directions because it's spherically symmetric. And it decays so much that all of a sudden you get to some value of r, and there's no probability density. And then, as you get to larger values of r, well, the probability density increases again, right here. Right? And then it finally decays as you get to larger values of r. What this wave function has in it here is something called, a node. There is a value of r right in here where there's no probability density. That value of r in terms of this constant A0 is 2 times A0. We call that a radial node. You can see that radial node very easily if you look at a plot of the actual wave function. So we're not squaring the wave. This is the wave function. Here it is. Here's the form for it. At r is equal to 0, it's some finite large value. And it decreases. It decreases till we get to a value of 0. Psi is equal to 0. Let me, just so that everybody, whoopsie. Let me just draw that here on the board. All right? So I'm plotting here the psi 200 wave function, the 2s wave function. I'm plotting it as a function of r. What it looks like is that at r is equal to 0, starts out at some high finite value, and it drops. And it actually goes through a 0. And it drops, and it keeps dropping until some point and becomes negative. And then it turns around and it approaches a 0 again. And so at very large r, the wave function is 0. Right here, right, where this wave function becomes 0, that's what we call a radial node. R equal to A0. This is a radial node. It is a value of r that makes the wave function be equal to 0. So if you wanted to solve for the radial node, you would simply take the functional form for 2s, which is 1 over 2 pi A0 cubed to the 1/2 times 2 minus r over A0 times e to the minus r over 2A0. If you wanted to solve for the value of r at which this node occurs, you set everything equal to 0. You solve for r. This goes away. This stuff is just a constant. It goes away. You have 2 minus r over A0. Hey, that's equal to 0. You can see when you solve this that r is equal to 2A0. That's the value of r at which you have a node. All right? Now, notice this. At r equals 0, at r equal 2a, naught, the wave function changes sign. It was positive up here. It's negative down here. That is a general characteristic. When the wave function goes through a node, the wave function changes sign. Hey, why is that important? Well, I think maybe in high school, we haven't talked about p orbitals yet, but remember you put sometimes a plus sign on a p orbital and a minus sign on a p orbital, right? Did you do that? Yeah? Well, that plus and the minus represented the amplitude, the sign of the amplitude of the wave function. Plus meant it had a positive amplitude. Minus meant it had a negative amplitude. That's what it meant. Sometimes you may have called it the phase of the wave function. You know why that's important, the phase of the wave function? It's important because when you go to do chemical bonding, when you bring up two atoms and you are overlapping two atoms and you're overlapping the wave functions that have the same sign, hey, you got constructive interference and you have chemical bonding. If you come in and you overlap two wave functions that have opposite sign, you got destructive interference and you've got no chemical bonding. We're going to see that later, but that's why that's so important. Okay, is the amplitude of the wave function here and these nodes. All right. Let's look at the 3s wave function. Here we are. Back up here. Plotted the 3s wave function, the probability density of the 3s wave function. Again, what do you see? You see right in the center, probability density is the largest. And then as r increases, the probability density drops off. However, you get to a value of r right here where you got another node. Another value of r that makes the wave function be equal to 0. Right? And then as you increase r, the wave function, again, the probability density increases. Right? It increases because look right here. Right? You're getting a more and more negative value. If you square a negative value, what you're going to get a large positive value. That's what this high probability density reflects. It reflects the fact that the wave function right in this area has a large negative value. You square it, you're going to get a large positive value. And then as you increase r again, well, again, you get another value of r where you have a node. The wave function goes to 0. Here's that point right there. Here's psi equals 0. Wave function 0. And then as you increase r, well, again, as you increase r, thank you. Again, as you increase r, right, the probability density goes up. Why? Because the wave function increased right there. See that? Square it, it's going to go up. And then it turns around, goes to 0, and this decays. If you wanted to solve for this radial node and this radial node, which I'll let you do, you take the functional form, set it equal to 0, and solve for r. That's easy. All of this stuff is a constant. This goes away. It's just a quadratic. And you're solving for the roots. Right? Okay. So, what have we learned? We've learned that the 1s wave function, 2s wave function, 3s wave functions, and in fact, all s wave functions, or L equals 0 wave functions, all of them are spherically symmetric. They have no angular dependence. Remember we said that in general the wave function depends on r, theta, and phi. S wave functions have no theta and phi dependence in them, unlike p wave functions, which we'll look at very soon. All right? Also, very important here, the probability density of all S wave functions is a finite value at r equals 0. Okay? Those are the two important things, and you know how to solve now for a radial node. You set the wave function equal to 0 and solve for the value of r that makes the wave function 0. Okay, now we have to continue this discussion so we can start to talk about the probability of finding an electron some distance from the nucleus. We just talked about probability density. We haven't talked about probability yet. And here comes probability. We're going to plot something, and we're going to talk about something called the radial probability distribution. What's that? Well, the radial probability distribution is the probability of finding an electron in a shell. You know what a shell is? You know, a shell is a sphere, but the sphere is hollow, except that, you know, at the diameter, right, or at the circumference, you have a thin coating. That thinness has got a dr to it. All right, it has a thickness to it. I'm sorry. It's a probability. This radial probability distribution is the probability of finding an electron in a shell of radius r and a thickness dr. So let me try to explain that some more. Here is this gray part. That's my probability density that I drew before, the dot diagram. This is a 1s wave function. This is the probability density for the 1s wave function, psi 100 squared. This blue thing here is a spherical shell. It has some radius here, r. It also has some thickness, dr. You see I cut away here, this thickness, dr. The radial probability distribution is the probability of finding this electron in this spherical shell that is of radius r and thickness dr. So it's the probability of finding the electron at some distance r to r plus dr. That's the radial probability distribution. Now, I want you to notice what is the volume here of this spherical shell? Well, that volume is just 4 pi r squared, the surface area of that spherical shell, times the thickness, which we're going to call dr. That's the volume. So now, if I wanted a probability of finding my electron in a S wave function, some distance from the nucleus, some distance r to r plus dr, what am I going to do? Well, I'm going to take my probability density, which I said was psi squared, probability per unit volume. I'm going to multiply it by a volume. Then I'm going to get a probability of finding my electron some distance r to r plus dr from the nucleus. And that's what we're going to talk about on Monday, is the probability, the actual probability of finding the electron from the nucleus. Okay, see you on Monday.